Okay, good evening, everyone. So, we will start with today's first session. It's going to be let me first introduce myself. So, I am G.R. Krishnachandra, an NPTEL PMRF TA for this course on computational continuum mechanics. So, I am doing my master's, my PhD in aerospace engineering at the Indian Institute of Science, Bangalore, in the Department of Aerospace Engineering. Okay, so in these tutorial sessions, I would basically be dealing with. It's meant more of a support or says some sort of additional doubt clearing sessions on some of the topics that are being discussed in this course. And this is going to be a weekly tutorial session. It's from 6 to 8 p.m., which you have all of you been informed of through email from NPTEL, what you call the coordination team for this place. So in every lecture, in every tutorial session, what I would be doing is I would be first reviewing the basics of or reviewing the concept that were discussed in the week previous to uh, or I will just mention which week we are going to discuss on, and and then we'll be following it up with a host of questions and solving some examples and some practice problems, which is very much related to the that particular week's assignments. Okay, so let's begin with today's session. So in today's session, what we would be doing is we would be reviewing continuum mechanics as to what continuum mechanics is and the wide usage of this particular very rich branch of mechanics and also of maths, so to speak. And then we'll be discussing about some concepts about linearity, when it is used, why it is used, and the properties of a linear system. And then we will be following it up with just describing the notion of nonlinearity. Why do we need to incorporate nonlinearity into our mathematical analysis? And broadly, this all in the present. I mean, this the present all the nonlinearities which are especially found uh, in solid mechanics. And and finally, we'll also be discussing about the different types of nonlinearities and some example situations in which they occur. And after that, we would be just going through some MCQ-like questions, which is very much the format in the assignment one of this course. Okay, so let's start with continuum mechanics. What it is, and continuum mechanics. So broadly, quantum mechanics is if we go by word to word meaning, it's just the study of the mechanics of continua. The continua is the keyword here. What do you mean by continua? So continua is when we consider any material to be uniformly distributed, in the sense that the mass or the particles which form the material are not considered to be discrete. So essentially, keyword is continua here, or sometimes also write it at continuum. But yeah, you get the idea. So continua is essentially when a material is considered to be not composed of discrete, to be not composed of discrete particles, but as if it is made up of composed of as if it is or formed of, you can say, mass which is continuously distributed. So that is the main thing here. Now you'll ask, why do we assume this? I mean, what is the basis behind it? Now, why do we deal with this? The thing is, let's just consider, say, the simplest thing you can imagine is just consider a block of wood. Okay. Now you know very well that wood is again a dense object. So what you say is, if we try to analyze this particular body, considering as if it's made up of discrete particles, then there will be trillions of particles, and we cannot use that what we call so far that we have learned what is known as the particle mechanics. Particle mechanics. Right. So we won't be able to use the theories that are derived from particle mechanics, or considering that particles from this would, because the thing is we won't be able to solve a system of equations which is and have equations for trillions of particles, isn't it? So what we do is we do uh, some sort of a statistical analysis. So quantum mechanics is very much like as if it is we are just considering analyzing the statistics of a group of particles, such that now you choose that block of wood. Now let's just bring let's try to explain this thing first. You have this block of wood, right, or a slab of wood, or whatever you would call it. It's just a block of wood. Now what you say is of dimensions, if you, since we are engineers, we always want to have dimensions. So consider it to be just 10 centimeter cross 10 centimeter cross 10 centimeter. I think this is. Now what you see is, now let's divide this block into furthermore in terms of smaller blocks. Now what we do is we just break this down into 10 equal intervals along all the three axes. So what I'll do is X, Y, and Z, let me draw it, and then 10 equal intervals in all these axes. And say we have some cutting machine, and we are able to break it down into, say, 1,000 blocks of 1 centimeter cubed, or 1 centimeter cross 1 centimeter cross 1 centimeter. These are the dimensions of wood, isn't it? Now here also it will look very much as if it's a monolithic system, isn't it? However, if you further divide, say you pick up 1 centimeter small, it's just a sub block, and then further divide it into smaller and smaller blocks, and you do it, say we now divide again, say 10 intervals along each axis. So we have 1 by 10 centimeter, and likewise, so the length progressively becomes 1 by 10 centimeter to 1 by 100 centimeter to 1 by 1,000 centimeter, and likewise. Now you'll find that at one particular instant, you will see that you are unable to go further, in the sense that now it doesn't anymore look like a block, isn't it? So don't take it literally. It's just I am just trying. I just want you to imagine that you go on cutting and cutting. At one time, it will seem that all the blocks doesn't look it looks very different from one another at one time, and then the thing is, we would no longer have a block. Also, it will just be particles, and that only exists in our imagination, because it may or may not be able to cut to that level. Now what you see is at that point, what we call is it the study becomes a particle like study, isn't it? At one point you'll have a block. You won't have a definitive block, but it will be just as if it's composed of particles. And yeah, it exists just in imagination. But yeah, so what you do is we don't go till that level. So if I ask you that, okay, so we had started to say that what we call that it's formed of mass which is continually distributed. But you would ask me now it's not continually distributed, right? Because there will be a lot of voids at that level. So the thing is, continuum mechanics is not meant to study till that level. Okay, so let me just draw a graph. I mean, just draw a small some say a particle size and mode of study. I think that should simplify it. Say, let's go from this. Let's take to be some. Say we had started with 10 centimeter, right? 10 centimeter. Now, as we progressively keep on dividing that blocks, at what particular we won't have exact exact separation line, but at one point, what you will have is till this time you will see that the material is still homogeneous. Now I'm just giving a new word. Okay. Homogeneous means the material is equally, I mean, uniformly distributed in that particular block. Till one time you will see that. After a while, you will see that this particular homogeneity starts breaking down, starts breaking down, and then eventually, it's just becoming more and more particle-like nature. So the thing is, you will consider our study or the mode of study, as I have mentioned here, to be till here. It is. The mode of study of that particular material is continuum mechanics. Okay, so we have a participant. Hello, Pawan. Could you please unmute and just introduce yourself so that anyway, I'm just alone here, so I think that would be a good way. Or if you are unable to just type something, I mean, just type it out if possible. Hello, Pawan, could you please unmute yourself and just introduce yourself, just in a very informal way. Am I audible at least? Hello.
Hello.
Yeah. Yes, Pawan. Good evening. Yeah. Can you please
Yes, sir.
introduce yourself? Yeah.
Uh, and I have joined this course, sir.
Yeah.
So right now I am working, and
Okay.
like it's useful for like in my field. So
Okay.
I'm expecting like I will get some idea about tensors and all
Okay.
because my
Yeah. We'll surely go there. Yes. Yeah. Okay. So in which areas do you work in? Just to.
mainly, sir, non-linear structural analysis, like soft matters and all.
Okay. Which all tools do you use during the analysis?
Right now,
Yeah.
for non-linear, we are not doing anything. So only we are doing this elastic thing based model only. Simply like we will get some Like whatever we do for metals, that thing only we are doing. So nothing great we are doing for nonlinear. So
Okay,
for
okay,
that, I am like that is my expectation from this course.
okay, okay, okay. So may I know which particular background do you hail from in academically, like which?
Sir, right now I am pursuing my aerospace engineering from IIT
Okay,
Madras.
okay, okay. You mean which masters or bachelors or?
No,
Uh,
PhD.
okay, okay. And under whom? Just like I
Uh,
have been to IIT Madras, so
oh, Professor HSN Murthy,
HSN Murthy. Which department? Mechanical or
aerospace, sir.
aerospace? Okay.
Ah, you know mechanical, sir?
No, sir, I don't know that much, but aerospace I have been to.
Okay,
I mean, during an
aerospace.
internship, yes, yeah. It was with Professor Santanu Ghosh and
Oh,
Ranjit Mohan.
अरे वाह. Okay, okay. Yeah,
Yeah.
I know them, know me, but I
Yeah.
know because year back only I came from there.
Okay, okay, okay. Yeah. So,
Yeah.
which particular area have you? I mean, is your focus of research as of now?
Sir, just now I have completed my company Viva. So,
Okay,
like
okay,
structures only, like I will be doing, but topic yet to be decided.
okay, okay, okay. Yeah, yeah. Okay,
So,
but
this,
broadly, which particular field does the professor work? I mean, HSN Murthy.
like mostly he is doing in area of contact mechanics, typology, and all.
Okay, yeah, yeah, yeah. Okay. Recently, I had met a professor, but I mean, I mean, do you have any friends in applied mechanics department?
Oh, okay. In applied, yeah.
There is one person called L Dhos. He's I think working under BSB Patnaik.
No, sir. That because earlier that AM was just above the aerospace, but
Okay,
now
okay, no, but
and
the
now they
building is
yeah.
is it? Okay, okay, yeah, then it's not, not very much possible. Yes.
So friends, no, but okay. Now I don't remember because of
Okay,
course the common na, sir. So in that I have met them. So like
okay,
done that elasticity course. So in that
okay,
friends were there. This
okay,
continuum I could not do there. So that is why I am trying to learn from here.
okay, yeah, yeah, that's yeah, many a time NPTEL helps us to, I would say, augment our knowledge in many ways. Many a time
But
we don't exactly guess the courses in our departments also, right? So
yeah, because
yeah,
that goes.
yeah.
Uh, Only thing, sir, just like whatever sir has put the references, those just I am telling personally, those are kind of high level. Like I could not get anything. Like
Okay,
he has recommended three books, so FEM by Beth or something.
yeah, yeah.
So
Bathe is yeah very much.
that
It's
is
I would
that
say more of an implementation point of view rather than actually understanding it.
I know, sir.
That's
That book.
that's
Other
yeah.
two, one the I writers I don't remember. One is advanced nonlinear solid mechanics, something like that. So that
Okay,
is thing above my head right now.
okay. Which book is it? I mean,
But
we could
I
always
think,
discuss through these tutorial sessions every week. Like you mean by A.F. Bauer? Huh?
yeah, yeah, yeah. Yes.
Okay, okay. We can always discuss the relevant sections if you I mean if you are agreeing to that, yeah. Like
Okay.
some of the
Because
topics we can always review through these I mean through these tutorial sessions every week.
I understood that appendix only. Like in one, it has been like a scalar vector. In other, it was a tensor. So just I could get that part only. Other maybe like with respect to time, I may get some idea. But
Yeah, yeah,
right
yeah.
now,
It always happens, right? Right, yeah.
I
Yeah.
will be working on that. Okay. And one more thing I wanted to ask, like after this course, like coding section is also there, sir.
Actually, in this, since the thing is, I'm not what you call a truly TA that you can call in. I'm
Ah,
more of a separate like TA, like uh, not directly associated with the professor. So I may not know the actual flow, but but the thing is, if it's possible, I may try to frame it like that also, since the tutorial sessions are fully. I mean, if you want it, we can always find a way out. Like we can also have coding sessions and all.
okay, sir.
At least I'm a bit comfortable with coding and also yeah.
Great. Okay.
Like we can always discuss some coding related issues. Like have you ever solved even simple nonlinear problems? I mean, by any
No,
chance?
no, sir, not at all.
Okay, not at all. Yeah.
Not
Okay,
like
so what we'll do is, yeah, in next session, actually I had a problem in mind, but thing is today is supposed to be just basic introductory, this one class. So actually I didn't think of including that today. It's just a simple, solving a simple trust-like problem, but using nonlinear approach. So that involves what we call as geometric nonlinearity, which we are going to discuss in this particular week.
okay,
So there, the thing is, we cannot use the very traditional methods such as Newton-Raphson approaches. So what we do is we use some technique called arc length approaches. So wherein we can model something very non-intuitive deformation pattern. Like if I should just what do you call give you from let me recall the problem. So the problem goes something like this. If you look at the screen, so the problem goes something like this: that you have a truss problem pinned here as well, and this pinned with a roller here, and this fixed. And we are applying a force. We are applying a force here, F, and then want to track how much it has moved. What you call the displacement from the original. What you call as U.
I think sir has also like simply does this problem in while teaching this geometric nonlinearity.
Yeah, yeah. So what we are doing is we'll actually solve it, not just discuss. We'll solve this problem. So
Okay,
we'll do this next week. I'm sure, yeah,
okay.
we'll do it next week. So essentially, we are trying to get this relations between F and U, and it goes as something like this. It starts like at 0 force, 0 displacement, and then it has some sort of this like behavior. So it goes down and then comes up again. I'll show you. I think I have just got messed up with the force and displacement. So let me just have the graph. So this some graph goes like this actually. I think F may be on this side or F or U or F or U. I don't actually recall, so I'll just yeah, we'll discuss in this, and we'll derive a nonlinear equation which actually tells that even though this problem looks very simple, it's very complex in terms of the equation that we get, that we need to solve it, and at the same time we are unable to do using the traditional Newton-Raphson approach. So what it's usually done is we just have something known as, since the thing is with the problem with Newton-Raphson is if we increase our load, say, okay, let's call this load F, and this, if we increase our F, we get a new value of U. But at till this point, we'll follow this curve. But after this, if we increase the load, we'll actually jump directly to this part of the curve, and we'll
Okay,
follow this line. So which means that uh, this region is inaccessible to us using Newton-Raphson method. So
okay,
what we do is we use a technique called as arc length approach. So in that case, we will have both increment and in force and increment in displacement as unknowns. So if we go till this, it goes it the method works as if we are using Newton-Raphson, and then what it does is then it tries to have change in displacement so that we actually start following this curve, and that it does automatically. You don't need to do anything. That's inbuilt in the algorithm. And then it will follow back and then just take the entire. So it gives us the entire displacement history with respect to load. So the thing is, what's happening here is this part that I have marked in that I'm marking again in red. This is in unstable. This is the unstable configuration. So we won't be able to observe this in any what you call an experiment if we do on this. So that's the thing is Newton-Raphson only captures the stable parts. The stable part is still here, and then till this part goes still here and jumps and go. So this jump is known as what we call often in structural mechanics and all that, some bifurcation, isn't it? Some bifurcation. So it just starts here and goes till it jumps very fast with a very fast dynamics, and then so this it essentially what's happening in our system is bifurcating from one state to the other, and this you'll find in books it's typically referred to as snap through bifurcation because it's snap through, since it's snapping from one stable to the other stable what do you call configuration. So that we'll discuss in the next class. I'll actually prepare my notes and then yeah, we'll discuss it. So you're
Sir.
mentioning about this book, right? So which section are you? I mean, have you mentioned this about this applied mechanics for of solids?
Like third reference is there, na, sir?
Yeah. I have opened it. Yeah. I mean, which particular?
Like I could understand appendices only. I am not
Okay.
like able to understand main chapters.
Okay. Sure. Okay.
First, I have downloaded but not seen. So first, I will not.
Okay. It's all right. It's all right. Yeah. We can always figure it out during these tutorial sessions.
Okay, sir.
And since we are both in PhD, I don't think you should call me sir. Just call me by Krishna. I'm again just almost done with my second year.
Okay.
Yeah. So what should we discuss today? I mean, we are just two of us.
Actually, I came to hospital for some work, sir. So I thought I will join. So many people will be there. But okay, we saw like I was the only one. Sir, I will also be prepared in the for the next tutorial session, sir, because once I will because from like week two, like
Uh,
mathematical part is starting. So I think
yeah.
that
That's the thing. That's the thing.
yes, sir. So I think
That
next tutorial will be very. I feel that will should be very good.
yeah. So what today let's do is we'll just let's just review the entire what has been taught in first week, because I think there is a lot of material in the first week, a lot of theoretical material because essentially it's theory which builds up, right, which builds up the main crux of this subject. So we'll just discuss. Actually, I had started with describing what is continuum mechanics. So the thing is, as
I
I
request
have
10 minutes break, sir, because I'm in hospital. Just I will,
okay. Sure. Yeah.
if will not, I will just go and come again.
Sure. Okay.
Till what time it is there, sir?
We'll be running till 8 p.m. Yeah.
Okay, sir. I will take 10 to 15 minutes, sir.
Sure.
Okay, sir.
Okay. Yeah.
Thank you.
Yeah. Welcome. Okay. Okay. Say I was talking about the which mode of studies should be preferred for which particular reasons of the material distribution, right? And as I had mentioned that I had started with 110 centimeter dimensions in all the three axes, length, breadth, and weight. Sorry, length, breadth, and width. So what we do is we'll just cut. Let's just in our imagination, let's try to cut it into smaller cubic blocks. So what happens is, as we keep on cutting it to smaller and smaller blocks, at one time, at till one time, you'll see that okay, the material distribution is fairly uniform. Okay. However, after some time, after a particular length scale, the thing is, you see that all the blocks do not look identical. Okay. And that's purely in our imagination. Okay, because we all know that all matter is composed of atoms, isn't it? So the thing is, till the time it is all the blocks are uniformly distributed, till that the length scale of that particular block is till where our the hypothesis of continuum mechanics holds. After that, it all becomes discrete mechanics or discrete particle mechanics or whatever you call it. There are multiple names for it. So it's just about they are just discrete particles, and then we are no longer able to use. And then for all this, we use some sort of what you call in various like atomistic modeling and all. Okay, but our concentration is fully in this domain, and that is where the theory of continuum mechanics holds, or the hypothesis, or whatever you call it, holds. Now, you'll ask me that why do we do what's the basis of the continuum mechanics? The thing is, we have made this fundamental assumption of the material being uniformly distributed, or the mass being uniform in the sense that there is no void. That's what I mean. I think I should just clarify myself that uniform means here what I'm meaning is without void, or rather it's more accurate to say continuous. Okay. So it's like continuous mass distribution. I think that is a much better word. Continuous mass distribution. Okay, and which means that we are not considering any void. Now I'll ask me, okay, but what's the advantage of having a mass without any voids? The reasons are even the reasons is actually that the thing is it helps us greatly. If I mean greatly, the thing is we are able to subject our analysis or the object of our study to various different mathematical treatment, because the thing is mathematics is very much developed for what you call a continuous system, or what you call as that and at the cost of giving you new words. The thing is we are able to have some sort of a field, in the sense that we have a distribution of some quantity over at every point in that particular object. Now we can use the principles of calculus, real analysis, function analysis, and subject our, and make our analysis very robust and very predictable. And it's uh, and that's the best part actually, that we are able to use all the well-developed mathematical tools to analyze. So that's the thing. So in essence, what I'm trying to say that having continuous mass distribution actually helps us greatly in our analysis, and we are able to build very strong foundations to study a system, in this case what you call material system. Okay, so the thing is, we'll ask, okay, but what is where all can we apply this continuum mechanics? Now continuum mechanics applications. It is used to study solid mechanics. Again, solid mechanics happens to rather it's just we call it, let's call it branch actually. branch of solid mechanics, branch of quantum mechanics, solid mechanics. Then you have fluid mechanics. Then thermal, uh, thermal studies, but you can also have something as heat and mass transfer. And yeah, there is a, it's not very nascent, but there is a field in magnetism which also involves concepts developed in quantum mechanics. That's what we call as micromagnetics. So micromagnet is the study of magnetization over a particular body using all the tools that have been developed, or using the tools that have been developed in quantum mechanics. So this is one new thing that you have just come across that was not discussed in the week one of this course. And then this solid mechanics again will have multiple sub branches. Fluid mechanics will have some branches. Heat and mass transfer also may or may not have sub branches, but yeah. So essentially, these are the branches of quantum mechanics. Now, what we do is let's just go to the second part of our discussion, which is to be on linearity. Sorry. Now, I'll ask me what is linearity next time. Okay. So the linearity is the sense. The most fundamental definition is that the concept of linearity is has to do with the relationship between input and output. Okay. So it simply says that linearity is based on two, what we call two aspects. The first aspect is what we call as additivity, and second is homogeneity. This is the relation actually. I'm just talking about what is in how is input related to output. Additivity says that if you have x1 giving an output y1 and some input x2 giving output y2, and there's some transformation which is going on, okay, is some what do you call, I would just call it function rather than a relation here. X1 gives y1, x2 gives y2. Then additivity says that then this implies that x1 plus x2 should give us y1 plus y2. Okay, this is what is known as the principle of additivity. And the principle of homogeneity says that if we have an input x1 which gives us an output y1, then say our input is scaled by some factor k into x1, then this should scale the output in a similar fashion, such that if it's x1, then it's also ky. So these are the two fundamental properties which is defined under linearity. And these two combines to give something known as superposition principle. Sure, you must have heard of this. but this two combines to give us superposition principle. Now, the superposition principle, what it says that for a linear system, okay, I'm just introducing the word system, but here we can say function to be also system, because ultimately it's system which takes an input and gives output. Okay, so the superposition principle says that uh, that if if a linear system is provided with various inputs, then the output will also be a sum of the corresponding outputs for every individual individual inputs. So that's what the principle of superposition is. I am sure you must have heard of this principle in Fourier series, or what do you call, sorry, when you do some sort of solving a heat problem or heat conductivity problem uh, using this Fourier series approach. That what you are able to do is you are able to add different uh, modes to form a general solution for the system. So that all follows from the system, or the principle of, or the principle of linearity. Okay, so essentially that's what it is. And then the net effect of these two superposition principles says that if you have a system A, suppose say we have a system A. I'm just writing script. Okay. Now the system A, if it takes an input of A, A is a scalar, U is the actual input, plus B, and V is the actual input, then this should give us A of U plus B, A of A. So this is what our linear, what do you call, the superposition principle essentially says. Okay. Now in solid mechanics, uh, how do you define a linear system? So I think we had discussed in our session in the week one lectures. What is linearity or linear system in solid mechanics? So this linearity in linear system in solid mechanics. Okay. Now let's start with force. Okay. Force. Then due to force, what we have? Say we are subjecting an object or a system or a structure to force. Then what is developed inside the material? Stress is developed, because stress is the internal resistance to any applied force, isn't it? This stress leads to strain or causes strain in the system. Strain is nothing but deformation in the system. These are all going on internally, and this is eventually what causes displacement. So here force is a global in the sense that we are applying over the body, isn't it? And stress and strain are local quantities in the sense that they are produced at every point in the material domain. And displacement is again the manifestation of the effect of force on the body. Okay, and this is also global. Okay, nice, we find then what? The thing is, linear system in solid mechanics implies that if say you have you apply force, and say you have scaled the force by some quantity, then stress should also increase by the same amount. So the relationship should be linear. Likewise, if you increase stress, and the thing is, yep, accordingly as stress increases by the same factor, this should also increase strain by the same factor. Likewise, if strain, okay, so the thing is, it should always also lead to displacement increased by the same factor. So that is what is linear. So the thing is, the relationship should be linear at every instant, from force to stress, stress to strain, strain to displacement. Then we call as a it to be a linear system in soil mechanics. Now you ask, what are the advantages of a linear system? What are the advantages? Because why are we talking about linear systems for so much? And why do we prefer linear system? Linear system has multiple benefits actually. And the first benefit is it's easy to solve. And again, what does an engineer want eventually? He wants some problem which is easy to solve, isn't it? So if the system is linear, then it's easy to solve. And you can just construct a matrix system, because the thing is then it leads to something known as X is equal to B eventually. So we have some linear system, model it, do some mathematics on that, or some numerical techniques, mathematical techniques. You get X is equal to, and you know X is, you just have to solve this X is equal to, there is a matrix X and B are vectors. So and then this gives a solution. X. And then do whatever we want. That's ultimately X is all these. If you are say trying to solve the displacement for a body, then X is this displacement vector. It has the displacement of every nodes that was present in the discretized domain. And the second advantage is that it is also it has a it is well posed problem, and the solution is always unique. And last but not least, superposition principle holds. And what more do we want than the superposition principle holding, isn't it? That's essentially the quality of a linear system. Okay, this is fine, but you'll see, okay, then how is it useful? Right? The thing is, say, when we have superposition principle. The thing is, one particular, just a small example that I want to present to you is, say you have a beam, cantilever beam, as usual. And what we are doing is we're applying loads at two different points. Here, F1, F2. Now you want to know the deflection at this point. Displacement. And this is just the vertical displacement. We want to know the vertical displacement at this point. So what superposition principle says that this problem can be broken into two problems. Okay. And I'll just have this problem as, yeah, we have the same cantilever beam. And what we do is, let's apply the loads one by one. Yeah, one by one. F1 we are applying. After we have applied F1, this will result in some deformation, isn't it? So what we do is this deformation here, this we call U1. U1 is response, or to be just you can say that it's displacement due to, and plus there is, you can just start afresh and then have the same problem cantilever beam, and you apply the load F2 at its corresponding position. This will lead to, it will deform in a slightly different way. Will deflect upwards. And this one is U2. U2 is displacement. U2, isn't it? Now the superposition principle says that superposition principle says that that U is equal to U1 plus U2. So that's the require specific feature about this, that of a linear system fire mechanics, that you are able to turn the system or break down the system in a terms of individual sub problems, get the individual responses and add them up, and you get the total response. So that's what it says here. Okay, so what we do now is let's start with the subject matter of this course, which will, as essentially anyway, we are going to deal with nonlinearities. In solid mechanics, because solid mechanics happens to be our area of study for this course, or the area of focus for this course. Now I must go back to the figure that I had drawn. Okay, I'll just copy this. Paste it here, and then we'll try to analyze that what I'm trying to say. Okay. Now you see. In this figure, it captures let's just take a look here. When the strain and displacement are non-linearly related, non-linear, then it is what we call as geometric non-linearity. Now, when the stress and strain are related non-linearly, then it is material non-linearity. Okay. Now, what we'll have is, say if the force creates, or there is a nonlinearity due to the force. Now, what I mean by nonlinearity in the force is, say your force itself depends on the state of deformation of a system. Now you'll ask me, okay, tell me an example. I have a simple example here. Say you are holding a garden hose. It's a very simple example. You are holding a water pipe, right? Or garden hose, isn't it? Which you use in garden, and then the water spits out. So you are holding this. Now, as you turn this and the water ejects very fast, because of which you find some backward reaction or a reaction due to the water ejecting out, right? So the thing is, now if you rotate the hose, right, you'll find that the direction of reaction is changing, isn't it? So it's what you see something, right? That the force here depends on the state. The thing is, in this case, say the force will be like this, and then if you rotate it like this, then the force will be, the reaction will be in a direction which is just opposite to that of the ejection of water. So you see that the force is very much dependent on how or what the state of the water hose is, right? And that is what is force nonlinear. That's one example of a multitude of ways. Now the another, okay, you'll say, okay, tell me an example when it is, if, when it is actually beneficial. Now you must have heard of something like what we call thrust vectoring of a fighter jet, right? Now the thing is, the exit or the aft part of the engine has the tendency to change the orientation of the nozzle. As you change the orientation of the nozzle, the thrust vector takes a new direction. So these are examples of, like, the load is dependent on the, and so when you're analyzing such thrust vectored fighter jet, suppose you are analyzing it or just trying to study this numerically using some softwares, or then what you see is that the force that will that you will apply will always be dependent on the direction of the, or the orientation of the nozzle, because you have to apply some because that exerting a force on the body, so you need to study that, right? So essentially what you are doing is you have to apply a force boundary conditions which actually is dependent on the configuration of the fighter jet. So that's an example of force nonlinearity, right? So when force is nonlinear, when force is nonlinear and all, then you have force nonlinearity. Then there is also something known as displacement nonlinearity. Or not displacement, I mean, say you have boundary conditions, right? Because when you solve a solid mechanics problems, you need to have boundary conditions, isn't it? Now, if the velocity, if the displacement boundary conditions also depend on the nature of displacement, then what you have is displacement, or what we call as kinematic nonlinearity. And this is also known as boundary nonlinearity because of its nature, because the thing is, this nonlinearity is present because it's solely due to the uh, what you call boundary conditions themselves, depending on the displacement of a, or the deformation behavior of a system. This geometric nonlinearity number 1, material is number 2, this is number 3, and this is number 4. Okay. Let's go about all these nonlinearities, or the as we had mentioned here, the types of nonlinearity. Let's go one by one. Let's start with geometric nonlinearity. So essentially, what it says is that there is a nonlinear strain displacement relation. Okay. Now, one thing about since today we are not going to discuss the mathematical aspects, we'll just discuss about what it just from some simple what do you call examples. Now we'll ask you, where does it occur? Now it occurs when deformation is large. Let me start with a simple example. So you're given a cantilever beam, okay, and say you are this beam is subjected to a very small load. Say you are applying a small F. Then this will lead to very small deflection, isn't it? Small u. Okay. This is what we call as this just linear behavior. And in this case, the relationship between the strain and displacement is linear. Now you are given the same system. And you apply a large F. And there is one constant here that the direction and the magnitude of F should always remain vertically downwards. So what we call as dead load. Then what happens after deformation? It will say deform in a very, it will deform a lot. You see, right? It has deformed a lot. Now in this case, U, say the length is L of this beam, then U is of the same order of L. Sorry, I'll just call it that the deformation U or displacement U, the ratio is almost or of the same order L, order 1, which means the linear behavior is no longer seen. Now what you have is a nonlinear behavior between displacement and length. Oh, sorry, between strain and displacement. So this will be our object of study or our interest of study in this particular course. So this nonlinear behavior. Now I'll ask me, okay. So say we are using nonlinear analysis even if the load is small, will it be valid? The answer is of course yes. Why? Because linear behavior is a subset of nonlinear behavior. Otherwise, this is, let's just change the arrow. Oh, sorry, the previous was fine. Approximation. So linear behavior is an approximation of nonlinear behavior, and this is valid only if you have small displacement or a small deformation, and the stress and strain relationship is also linear, and the displacement boundary conditions are constant, and applied forces are constant, which is here also this is a dead load. So it means every individual relationship between all these components, right? Force, stress, strain, displacement, all are linear. Then yeah, so it's a linear behavior is a special case of nonlinear behavior. Now let's move to the next nonlinearity in our discussion here. Then what comes as material nonlinearity. And material nonlinearity actually has to deal with what we call, this is when the stress, I'm stressing on the word strain, but yeah, the stress strain relationship is nonlinear. Okay. And this is you'll see this behavior in there are again different types of material nonlinearity, and they are clubbed into various subcategories called, say, hyperelasticity. Then you have plasticity, viscoelasticity, and likewise viscoplasticity. Okay. Now you also find these are different terms that how do you explain it? The thing is, let's consider you have a rubber band. Okay, rubber band. I'm considering a rubber band. Okay, this is a rubber band. Say you have a rubber bracelet, right? And you just make a cut and spread it out. It becomes a flat plate, isn't it? Or flat ribbon. Now what you do is you just pull it. I have used the wrong direction here. Just pull it on both the ends, and you are able to stretch it to a large extent, right? And there is one thing about rubber, and if you draw its deformation, it's sorry, stress and strain relationship, stress and strain, then it will be something like this. You see, right? It's not linear. It's not the curve is not linear. It's not a line, isn't it? So this is one such example of material nonlinear system. The thing is, you are clearly able to see that the stress and strain relationship is not linear. And yeah, rubber is the study of rubber is, yeah, then it's again comes under hyperelasticity. Now there are different meanings to every term, but let's not discuss it right now. Although I would just like to bring you to this concept of plasticity and all. Let's just discuss it. You must have read about or the stress and strain relationship for an aluminum object, right? Or aluminum cylinder you have, and then you some material test, some load testing is done, and you see that there is also necking phenomenon and all. So it's linear to some extent. Then it becomes something like it reaches yields limit, proportional limit, right? Where eventually then there is some necking here, and then till it goes there, and ultimately it just fractures, isn't it? There's fractures here. So you see that the linear relationship is only to some extent. This is the linear part. This sigma and epsilon. Sigma is stress, and epsilon is strain. Okay, and this for aluminum, and just aluminum. So this portion is what is studied under plasticity. Okay. And this is again study under quasi-static loading, in which you are just gradually increasing the load. And if you are, say, changing the what you call you are having some finite load rate, in the sense that the load changes at some what you call finite value with respect to time. Then what happens is, then you also have dynamic effect coming into play, and then that's what you have viscoelasticity and viscoplasticity. It depends on the relative ratios of elastic aspect and plastic aspect of in that particular material. Relate again, it's based on relative importance or observations, if you call it that way. Okay, now let's go to the third part, which is kinematic nonlinearity. Well, as we find now what? So the kinematic nonlinearity has to deal with, as I had mentioned, right? It has to deal with one thing, which is that the displacement boundary conditions depend on the deformation of the body. Okay, so this is what is kinematic nonlinearity. Now, Leela's, okay, tell me some examples of such displacement when the displacement boundary conditions themselves depend on the deformation of the body. Okay, let's have an example. That's that was discussed in the week's lectures as well. It's what you call as contact problems, isn't it? Now, say what you have is you say you have some a flat bed, okay, and you have some say you have a sphere. This is a sphere made of made of rubber. Okay, and then you are applying a load on this. Now you see something, right? As you're applying the load, the rubber, this rubber sphere is getting deformed, and it's just flattening out. It's flattening out on the on this end. So in the sense that you see that the portion which is essentially there was just one point on of the rubber which was in contact with the flat surface. This is like I'll just call it rigid surface. And as you increase the load P, as you keep on increasing the load, it's getting deformed, and eventually it's just getting flattened over it. So you see that the area of the application of displacement boundary conditions is also changing, isn't it? The subset of the spherical surface area which is being subjected to displacement condition is changing, and it's depending on the displacement of the or the deformation of that rubber sphere, and that nonlinearity is what is kinematic nonlinearity. And yeah, and you very well see that it the thing is very much depends on the boundary and sorry, it depends. Yeah, very much depends on the boundary. And then you also have multiple subtypes of there are two subtypes at least. One is the thing is in this case, what you know is that the area over which the boundary condition is changing, that is, the area itself is changing, right? So the area which is gradually getting flattened is also changing, and also the boundary conditions changing along with it, isn't it? That is first thing. So which means that this is a very complex. This is a what do you call this? A complex nonlinear problem. And there are in some certain aspects what you have is that the area doesn't change, which means that only the thing is only the area will remain the same. It's just that you don't know the displacement boundary condition will keep on changing as you are changing the loading scenario. So that is a slightly milder nonlinear problem. Now let me just think of an example. Now, one such example was given in the lecture itself, that you had a small cubic volume. A small cubic volume, sorry, cuboidal volume. It's also some made of some rubber-like material, and then you have a slab over it. And you're applying some load here. The thing is, as you are keep on loading it, and then say you're also transmitting it in such manner then what's happening is on the upper surface, the area over which the boundary conditions are to be imposed remain the same. However, it's however the values of the whatever boundary condition applying keeps on changing. So that is what I was calling it as mildly nonlinear problem. In the same what do you call, for the slab or for the larger slab we have block here, as this upper block is moving over it, here it has this complex nonlinear problem. The thing is, the area of application of the boundary condition is also changing as well as the corresponding values. So that's what it is. Yeah. Let's come to the last boundary condition, last nonlinear what you call nonlinearity here, and it is force nonlinearity. And as far as you recall that it is dependent occurs when the applied forces depend on the formation of the block of the what do you call material, or the structure. Now, here typically you'll find several examples in the lecture. One was there were two examples. One was because of the say as the parachute is falling down, and the other is and the other one is when the other example was when you have some this or what is what here forgot that word it is the airbags, right, in the cars when there is an accident, then it just pulls off. So yeah, a car airbag deployment. In that case, also the direction of the forces keep on changing. So these are the two scenarios explained in the. And I had mentioned about a garden hose, right? And then you change the direction, and then the force, the reaction force also changes, keeps on changing. So all these are examples of force nonlinearities, isn't it? And the simplest example, if I would give it, is say you have a cantilever beam. Let me draw a cantilever beam. And say you have a load. As the system deforms, the load also deforms accordingly. So it's no, the load changes its direction accordingly. Okay, so you see that after deformation, even PS changes its direction. So this is what of also called as follower load. So the follower load makes the system non-conservative in nature. And yeah, so this is also tough to solve because the thing is this the force boundary conditions also depends on the structure or the structural deformation. Okay. So let's just review what has been discussed so far. So we started with a basic definition of quantum mechanics, why it's used, how it's used, and the limits, the scale limit of quantum mechanics, after which the hypothesis breaks down. And then we talked about the various branches of quantum mechanics, and these are some of the prominent ones. And then we explicitly mentioned that soil mechanics will be the object or the focus of study during the entire course, as was mentioned by the course instructor, Professor Sachin Singh Gautam. And there are several branches, as you see: soil mechanics, fluid mechanics, heat and mass transfer, micromagnetics, which you may or may not be hearing it for the first time. But yeah, and then we talked about the principality, the linearity principle, if I call that, it's linearity principle. and the important properties of a linear the conditions for linearity principle to hold. And then there's two conditions called additivity and homogeneity or the condition leads to what you call as the superposition principle. And you very much knew got to know about the what do you call the significant or the advantage of the superposition principle. And then we talked about linear system in soil mechanics, because soil mechanics tends to focus a lot on forces. Your subject and structure to forces. You globally on the global scale, you see displacement. However, locally at every point in the material domain, there is what you call the internal resistance, which is called a stress. And because of the application of force, you see that the distance between two particles keeps on increasing or decreasing, or whatever the situation may be. So that leads to the strain. And then you see the stress and strain are local manifestations of the effect of force on the structure, and displacement is the global manifestation. Okay. And if every relationship between force and strain and every relationship happens to be linear, then only we say that this particular structure is undergoing or has a linear behavior, or is a linear system, isn't it? Also talked about the advantages of a linear system in the sense that it's very easy to solve, and because of that, all that we require is to form a matrix system X is equal to B and solve for X, and X will have whatever quantities we are looking at. And this linear system also mathematically it's a well-posed problem, and which ensures that the solution is unique. And the most important thing is the superposition principle hold. So which means if you know the response of the structure to one load, and also the structure response of the structure to another load, you actually don't need to solve the system, provided that the system is under combined loading, because the net result will just be the sum of the individual response. Okay, so that's what superposition principle, what you call, implies here. I shown you an example of this superposition principle in action. I'll just call this superposition principle in action. Okay. Okay. It's just a superposition principle in action. Okay. And then we'll talk about the nonlinearities in soil mechanics, and the types of nonlinearities here. You see that it's vertical force nonlinear. You started with geometric nonlinearity, then material nonlinearity, kinematic / boundary nonlinearity, and the fourth one was the force nonlinearity, right? And in every nonlinearity, there is a certain relationship, nonlinear relationship between quantities, right? In in geometric nonlinearity, what we saw is there is a nonlinear relationship between the strain and displacement. In material nonlinearity, there is a nonlinear relationship between the stress and strain. Kinematic nonlinearity, or what we call as the bonding nonlinearity, is solely because it's actually because of the fact that there are scenarios when the displacement boundary conditions to the structure is itself dependent on the deformation of that system. Okay, and that makes it complex. You can have multiple complexities, layers of complexity, when then the contact problem is known to be a very nonlinear problem. And force nonlinearity is when the what you call the nature of the force depends on the configuration of the deformation of the deformed structure. So that's what is we have what we call the force nonlinearity. So that I explained using four different. We went further into all this. Now what let's do is let's just do some MCQs for this problem for this class, keeping in mind the nature of the problems that we have discussed or that have been asked in week first of this course. Okay. All right. But the first question is which quantities constitute local effect? And the options are stress, force, displacement, and the fourth is strain. So the answer you very well know because we have already discussed it several times by now. The answers are stress and strain. Okay. Question number 2. Are linear systems special case of nonlinear systems? Then you must be recalling, right? The answer is yes. Why? Because linear systems are approximation of nonlinear systems. Okay, and that they hold only when certain parameters are very small. Okay, and say if there is very small deformation, then you can use linearity and then solve the problem, right? And I'll ask you one problem. Say which nonlinearity or which nonlinearities appear in the domain? Answer the options are, I mean, you have all the 4 options: material, geometric, kinematic, and force. So which one of these nonlinearities appear in the domain? Means it's, or which simply means that which of they are locally defined. Now, as you recall, it's the stress and strain which are local manifestations, right? Isn't it? So when you look at the relation between stress and strain, it is material. So you have one answer. The second is the relationship between stress and displacement. Sorry, the strain and displacement. It's also nonlinear. And strain being a local quantity, which is formed because of the local nature or the local change in the what do you call the relative position between 2 different material points. So this leads us to what we have one more geometric nonlinearity, right? So the answers are material and geometric nonlinearities appear in the domain. Okay. Now the question number 4 is are question number 4 is elastoplastic contact problems can be classified in the category of rough nonlinear problems. Is it true or false? I've just tried. Mm, true slash false. The answer is astroplastic contact problems can be categorized as, you know, that any contact problem essentially is complex nonlinear problem, right? Or rough nonlinear problem. So I think the answer is, the statement is true. Now let's go to fifth question. The statement says that in mildly nonlinear problems, stress strain relations are history dependent. The options are true slash false. In mildly nonlinear problems, stress strain relationships are history dependent. The answer is no, it's false. Because in mildly nonlinear problems, the stress strain relationships are history independent. So it should be independent. Then only you can have mildly nonlinear. Because the moment you have history dependence, then the solution algorithms or the solution techniques really become complex. And even the deformation pattern becomes complex, because the thing is, the strain and stress, the stress and strain uh, has a different relationship at different points in time. So it simply implies that it is going to a very nonlinear problem. Okay, it's not no longer mildly nonlinear. Okay, and let's have a sixth question. Does linear system involve large computational cost? Now you see, nonlinear linear system, when we solve a nonlinear linear system, effectively it reduces to a problem of solving a matrix system of equations which is given by x is equal to b. Now to solve x is equal to b, we just have to, yeah, that may require computational cost, but the thing is, it's just one time, isn't it? You solve it once and you get the result. However, for nonlinear system, you have to perform several iterations, because the thing is, in some case, you have material nonlinearity, in force nonlinearity, displacement nonlinearity, geometric nonlinearity. You have to iterate even the matrix system. So since A can be function of u, B can be a function of u, so you have to do iterations till you get the what I call the final answer. So which means that you have to solve the matrix system of equations multiple times, and that does involve large computational cost. However, for linear system, you just have to solve that matrix system once. Okay, so that is the answer is no, it doesn't. Okay, no, it doesn't involve large computational cost compared to nonlinear system. That's what the answer, the background of this situation is. Okay, now let's have a seventh problem. deployment of parachute involves geometric nonlinearity. True slash false. What will be the answer? So the answer, as you know, is what? The deployment of parachute involves what changes as you deploy a parachute? The thing is, as you deploy parachute, first the strings will open up, okay, and then it will gradually what you call get taut, okay, it will get taut, and then you have various small. I mean, it will just be some. It will cover some what you call hemispherical. It looks like some, I mean, hemisphere-like system, and then you have so from the point of the moment you started deploying the parachute till it's full, the strings are fully taut. You you see that it undergoes changes in something which is tension, right? The tension orientation keeps on changing of the string due to the strings on the on the parachute what do you call the main part of that. So the thing is, it doesn't involve geometric nonlinearity. What it involves is force nonlinearity. We are just sticking to what was discussed. Otherwise, you know, geometric nonlinearity does exist. I think I said. As I mean, let's just stick to what was discussed in the first this one, but uh, to what we have learned, it's false. However, if we see that, yeah, geometric, it is there, but the thing is, okay, I think I should just better delete this. So just it should be a yes question. Involve. I think there's related to force nonlinearity. Does deployment of a parachute involve force nonlinearity? Option is the answer is true. It doesn't. Okay. I think we should do one more problem before we call it a day. So, which are the following quantities? Or I think I should. Have let me just think of a question. Does a linear system involve deformation dependent loads? What would be the answer? The answer is obviously no, isn't it? Why? Because linear system is known to be, I mean, it's in a regime where everything is, so the force is independent of the deformation of the body. Okay, that's what makes it deformation. There should not be any deformation independent loads. So with this, I believe we can close today's session, and I think this is all I had to talk about for today. Okay, so what we do is, yeah, let's meet. We'll be meeting again next week on this at the same time, and we'll be discussing, reviewing the whatever was been taught in week 2 of the course. Okay, in this case, our overview was with regard to first week, first week of lecture of the course. So in the next tutorial session, we'll be discussing the second week of the course and also solve some slightly related problems which were has been asked in the assignments. Okay, so I think it's a good time to stop the session for today, and I'll just stop recording.